waves in motion. And you can see there it starts at the top where I'm talking about putting a rope on a doorknob and shaking it. And the thing is you shake that rope, it's going to be sending waves down that rope, but eventually as it gets to that doorknob, it's going to cause reflection to occur, meaning it can't go through that door or the door handle, so it ends up bouncing back. And when we get things that bounce back interfering with waves that are still coming in, sometimes you can get a standing wave created. And it says there a standing wave is any wave that appears to stand in one place, even though it's really going to be two waves that are interfering with one another. So I've got this simulation going on here, and as I go ahead and I look here, you can see the red wave, that's my initial one, is traveling along, and all of a sudden it's hitting this boundary over here. And all of a sudden now we've got this blue wave that's going to be reflected back. But notice the resultant here in the middle, which is going to be this black wave where it's alternating between high points, which are our constructive interference, and it's also rotating between what will end up being our low points right about now. Okay, so when we go ahead and look at that, we get this standing wave, and this wave, or when we look at that black wave, it appears to stand still. So what I'm going to do is I'm going to pause it on complete constructive interference. Okay, so when we look at a standing wave, okay, we need to identify a few things, and you can see some A's and N's down here. So I'm going to go ahead and come back to this. Your nodes, those are just going to be the pivot points. This is where the medium actually is not moving, it's just pivoting or rotating about a single point. And then your antinodes, these are going to be those high and low points on that standing wave. So when I look here, let's first count our antinodes, okay? And we said those antinodes were the high and low points. So when I go ahead and look here, 1, 2, 3, 4, 5, 6. So I have 6 antinodes on this standing wave. But let's go ahead and count our nodes. Okay, so there is one right over here, it's pivoting. So 1, 2, 3, 4, 5, 6, and 7. And I don't care what kind of wave you do, okay, or what kind of standing wave you are looking at. You will always find out that there is always going to be one more node than antinode. Okay, so just remember that, always one more node than antinode. Now I don't know if you've ever heard this where they talk about if you sing at a high enough pitch that you can go ahead and break glass. And the thing is, it is true, okay, and that's going to be resonance. Every single thing has its own natural frequency, where we talk about those particles in solids being extremely close together, and what they're doing is they're just vibrating back and forth. And as they vibrate back and forth, they themselves have their own natural vibration or natural frequency. But when we create a vibration that matches the object's natural frequency, what we're doing is we're basically getting a constructive interference occurring, and you can find out that that resonance is or can go ahead and break that glass. Okay, so I'm going to go ahead and play this here and just watch the glass as it is vibrating. And I went ahead and I sped it up to about 28 seconds because it's going to break at about 35. Okay, so just go ahead and watch the glass as the sound is being created. So again, as that glass was vibrating back and forth, okay, so you had that sound, kind of the annoying sound, but it's causing that glass to vibrate, and all of a sudden it's going to get to a point at which that glass cannot hold the threshold or that vibration, and it ended up breaking at about that 35 seconds, okay? So that's going to be resonance. So again, it's matching an object's natural frequency, causing constructive interference, which as it vibrates, it gets outside of the threshold of that object, and in this case the glass ends up breaking. The last section that we need to look at is going to be talking about earthquakes and talking about seismic waves. Okay, so when we go ahead and look here, okay, the waves that are going to be produced by earthquakes, those are going to be called seismic waves. And there are three types of seismic waves that we need to look at. And the first one is going to be a primary wave. And the reason why it's called primary is because when an earthquake happens, this is the first seismic wave that is going to reach the recording station as it leaves that epicenter. And it is the one that's going to travel the fastest. So a primary wave, this is going to be a P wave, or another name is the P wave, but they are actually longitudinal. Okay, so these are the ones that are going to be moving back and forth in the direction in which that energy is moving. So primary waves are longitudinal waves. Like I said, they are called primary because they travel the fastest and reach those seismic recording stations first. Secondary waves, these are ones that are going to be transverse. So again, this is that right angle motion. So the medium's moving at right angles in the direction, or compared to the direction in which that energy is traveling. The reason why they're called secondary is they are second to the primary waves. They are the ones that reach the recording station after the primary waves. So they are traveling a little bit slower. The key thing here is they cannot travel through liquids. Okay, so they cannot travel through the center of the earth because we know that we have that liquid core. The last type of seismic wave is going to be a surface wave. It's actually a combination between P and S waves, and the reason why we call it a surface wave is because it travels just along the surface of the earth, okay, or the surface of the planet in which we are looking. An example of a surface wave is going to be a tsunami, but the thing that is kind of important about those, they are the slowest of all of the seismic waves. But even though they are the slowest, because they travel along the surface of the earth, they are ones that do the greatest amount of damage, okay, when you think about those waves coming in and so forth. So let's go ahead and continue on looking.
P waves cause the ground to compress and expand, that is, to move back and forth, in the direction of travel. They are called primary waves because they are the first type of wave to arrive at seismic recording stations. P waves can travel through solids, liquids, and even gases. S waves shake the ground in a shearing or crosswise motion that is perpendicular to the direction of travel. These are the shake waves that move the ground up and down or from side to side. S waves are called secondary waves because they always arrive after P waves at seismic recording stations. Unlike P waves, S waves can travel only through solid materials. After both P and S waves have moved through the body of Earth, they are followed by surface waves, which travel along Earth's surface. Surface waves travel only through solid media. They are slower moving than body waves, but are much larger and therefore more destructive.
So we've concluded chapter 15 talking about waves. We talked about mechanical waves. We went through and talked about waves in action, and then we concluded with talking about earthquakes and their seismic waves.